So you're going to be putting water into your Petri dish. I know it tells you to what, eyeball 20 milliliters or so. Now, oh, station 13. Station 13, bring your 2 pencils and battery up to me, please.
No way. No way. Hey, they're not safe. I'm not playing Lieutenant. You got me.
Now, the beginning instructions tell you to put the electrodes down in the water and make observation. And if you read on down, it says you're probably not going to see anything. The reason why is because it's deionized water. Will the deionized water conduct electricity?
No.
No, because there's no ions to conduct the electricity. So here's what you're going to do. We're going to skip down a little bit. Your electrolysis apparatus. That's what this is. You should have the battery attached to it. And what you want to do is you want to attach the alligator clip leads onto the graphite of the pencil. One on one side, one on the other side. And make sure you're keeping track of the color because that's important to determine whether you're dealing with the cathode or the anode. Do you need one of these?
Yeah.
Here. Okay, now, so graphite makes it's a really good conductor of electricity. What? You just connect the tops.
No, I'm just making sure.
Graphite makes a really good conductor of electricity so that when you place these down into the water, when I tell you to, you're going to be able to force electrons through that water. Now, if you pay attention to what I'm drawing up here on the screen. So, you're going to have these electrodes, okay, attached to the 9 volt. I'm going to make this my anode, where the oxidation reaction is going to be taking place in my battery. This is going to be the positive, so this is going to be my cathode, where the reduction is going to be taking place in the battery. Now, if you remember, this battery is a positive 9 volt, meaning that the reaction that's going to occur in this is thermodynamically favorable. And we are going to be able to do work with the electrons that it produces. So the electrons are coming from the anodes. So we got electrons going in this direction, and they're going to be going into our Petri dish. This up here is an electrochemical cell. That's thermodynamically favorable. Austin?
Yeah.
Have a seat.
Okay.
And don't get back into the lab. This is what we're going to call an electrolytic cell. It is thermodynamically unfavorable. We are going to be forcing reactions to take place in the Petri dish that normally would not. They're unfavorable. Remember, we said that an unfavorable reaction, we would have to put energy in or work in to get it to take place. That's why we have this. So our electrochemical cell, we are going to use the energy that it can produce, because it's a favorable reaction, to force reactions that are going to take place in the electrolytic cell. Everybody okay? Who's got questions?
Are all electrolytic cells unfavorable and all electrochemical cells favorable, or are these examples?
No, they're going to, so a cell that's made that is considered an electrochemical, it's made with a reaction that is thermodynamically favorable, because the idea behind an electrochemical cell is to be able to do something with the energy that it's going to produce. And an electrolytic cell, always going to be, you're doing something, you're having to put energy into that to get the process to take place. Those of you in engineering, you made a thing that you use like solar cells to split water, right? And did you run something from that then? Ran a little car or something like that? So you made an electrolytic cell because you took water and split it apart into hydrogen and oxygen. We're going to do the same thing here. Okay? Now, one issue that we have right now, okay, I didn't know if I had water in there or not. So I've got water in here now. The problem with it is that for this thing to run, we've got the electrons have to be able to move through the water. And because it's deionized water, really the only ions that we have present in there are the hydronium and hydroxide from the equilibrium of water from its autoionization. Remember that? And the concentrations of those are 10 to the negative 7th. There's not very many ions. So the sodium sulfate, what you're going to do is add, I know it says 20 crystals or so, just it's chunked up over time. So if I put in like two chunks like that, can you guys see that? If I put in 2 pieces like that, that should be enough to take care of it. Okay? Hey, wait a minute. There we go. And then just use a clean stirring rod. Make sure you've rinsed it off. And get those two to get them to dissolve. Okay? Jonah, Austin, come up here, please.
Me?
Yeah, you.
What did I do? It wasn't me this time.
Oh, you were involved. You guys do remember that you did sign a contract at the beginning of the year about labs.
Yeah.
And not jacking around in it, right?
Right.
And I see you skulking around, ready to spray somebody in the ass with some water. And you, I'm not sure if you had yet, but you were looking like you were going to.
Okay.
All right?
Got it.
No jacking around.
Okay.
I don't care if it's just water.
Got it.
Get. You can go back in the lab now, Austin.
Okay, so the non-calcium portion would watch
So Joe, once we crystallizate this Mr. K, do you want us to like do the rest of this stuff in the procedure?
No, okay, class. So it looks like we're in procedure number what, 2?
Yeah.
Okay, so you got the stuff dissolved. You're going to put, I think it says 10 drops of universal indicator. It says univ end. Okay, it's bluish green stuff. All right. So it's going to look like, stir it around, make sure it's mixed well, you get a uniform color. Now, all you're going to do is, and you want to hold these as still as you can. So you're going to put the electrodes down in here. You're going to hold them as still as you can. Doing it against the white background is ideal. So I think a lot of people left out the white laminated things from last period. It's not out. I would suggest that you get it out. Now, you're going to see colors at each electrode, but I would also encourage you to get out the magnifying glass that you have in the back of your hardware drawer. Is Eli here? Yeah, he is. Thank you. And then look at the tips with the magnifying glass and make a comparison between the two sides. Oh, crap. Negative. Whoever's watching this video, I reversed that. Sorry. Just a second.
You're an idiot. We put it in the indicator. Wrong one. It says universal. Not the field of language. What happens if we just add that in now that we're... I don't know. Ask Mr. K. He's the chemistry guy. Mr. K, we messed it up again.
What'd you mess up?
They put in the fetal instead of the universal.
Just put in dump it out, start over again.
No, this was that. No, this is yesterday. I trusted you, Brian. Did you have it on? You should have known. I trusted you.
Joe, Evan, you guys were not listening to me.
We were looking for we're missing half our life.
What blue yellow do you not understand?
I didn't hear you say that.
Uh-huh. You weren't listening.
Joe, you just weren't paying attention.
How you doing, Maddie? Did you have a test last period?
Yeah, very, very good test.
Okay. Kind of like the acid-base test?
Sure.
All right. Now, Eli, pass. So, if we read through this now, you made your observations. The negative electrode. Both of them produce gases. Which one produced more? The negative or the positive? Negative. So you should have seen more. If you didn't see that well, just go ahead and put them back in there and hold them really still. That's why the magnifying glass is kind of required for this, because they're not easy to see. Okay? Now, the red and the reddish color and the blue purple color, those are pretty easy to see. And we're going to talk about those here in a second. You should have got the purple at the negative electrode, and you should have got the red at the positive electrode. Okay? Okay. Everybody got those observations? We're able to see the bubbles well now? Now, we're on number 4. It's use the color chart to the right to answer the following. The color of the negative electrode is purple, bluish, due to the presence of look at the color paper or the color codes. It's going to be basic. So what ions?
Hydroxide.
OH ions. So in my diagram up here and on my electrodes, remember I said this right-hand side is my anode, which is the negative side. And on this side, we have hydroxide ions being produced. Okay? Now, next part. The color of the positive electrode is red due to the presence of hydronium, or I'm just going to use H plus ions. Now, I know I prefer H3O over H plus when we're talking about acids and bases, but most reactions that you're given in tables and stuff don't use the hydronium ion. They're just going to use the H plus. Okay? Now, choose the answers. At one pencil tip, hydrogen ions being formed. The other pencil tip, hydroxide ions being formed. We need to explain this observation. Let's consider the negative electrode first. So on this side, okay, choose the answers by deleting what is not needed. Water surrounds the negative electrode, and now which one? Sodium or sulfate ions will be attracted to the negative electrode. Sodium ions. The negative electrode of the battery is negative because it is the battery. It's producing electrons. Remember, that's why we call it the anode, because the oxidation is occurring there. And this can force a chemical reaction to gain electrons. So, in our electrolytic cell, this side is going to be our reduction. So, in our electrochemical cell, we have an anode and a cathode. In our electrolytic cell, we have an anode and a cathode. And the anode and cathode still go by the same pattern. Your reduction is going to be your cathode. Your oxidation is going to be your anode. So in our battery, our electrochemical cell, our anode is producing the electrons. It's going to force electrons into a reaction that's reduction. This side of the electrolytic cell then is the cathode. Over here, we're going to have oxidation. And this would be our anode in the electrolytic cell. Okay? So keep in mind, the idea of our electrochemical cell is that we're forcing electrons through and forcing the reactions that are not favorable to take place. So we're forcing a reaction to gain electrons on one side, but then we're also forcing electrons to be lost on the other side. Now, scroll down and you're going to see a chart. Now, these are the four possible reactions that can be taking place. Now, they're all reductions, but two of them are going to get flipped to be oxidations. So these are the possible ones. Okay? Now, this has water as a reactant. You guys, that's over the thing. This reaction has water as a reactant. So this would have to be our reduction reaction if water was involved. This up here would have to be reversed and would be the oxidation reaction if water was involved. Everybody okay with that? Because what we're looking at here in our Petri dish is we have sodium ions, we've got sulfate ions, and we have water. Those are things that we're starting with. Those are our reactants. So if water is a reactant, this one's fine. This one would have to be reversed. This reaction right here, this has sulfate as a reactant, correct? Could this be reversed? Based on what we have in a Petri dish, can we reverse this reaction and still have that as a possible reaction? Sulfate is in our Petri dish, right?
Yeah.
That means sulfate has to be a reactant.
Right. So we can't reverse it.
Can this be reversed? No. Because if we reverse it, sulfate's now a product.
Yeah.
Now, so two of these are possible oxidation reactions. Well, this as a possible oxidation reaction where it's reversed, this can't be. We cannot have this reaction here as our oxidation reaction because if we reverse it, we have the sulfate as a product and not a reactant. So this reaction right here is really the only reaction that we could have that is an oxidation reaction. Now, both of these down here are possible reduction reactions because we have water as a reactant and we have sodium ions in the solution that could be a reactant. Now, based on your observations, which of these two is taking place? The water being reduced or the sodium ions being reduced? Max?
I'm pretty certain it has to be the water ions being reduced because no solid got formed.
You don't see any solid being formed. You do see gas being formed. So, if reduction is taking place in our electrolytic cell, if reduction is taking place, the two possible reactions are two waters plus two electrons, giving us a hydrogen gas and two hydroxides. That's a possible reaction. The other possible reaction would have been our sodium plus an electron, giving us sodium atoms. Because we did not see any solid being produced, and that would have been exciting if it was, that can't be our reaction. But you did see gas being produced, right? Not only that, what color did this side change to? Blue. Meaning what was produced? I mean, you see it here, right? I'm producing that blue color around that electrode. And that's my negative electrode. And blue represents what type of solution pH-wise? Basic. Oop. Wrong way. There we go. There we go. Oop, too much. So we have gas being produced and we have hydroxides being produced. This is the reaction that's taking place on the reduction or cathode side of the electrolytic cell, or the side that's attached to the anode of the electrochemical cell. Everybody with? Now if we go over to the other side, our possible reactions were two waters producing oxygen, 4 hydrogen ions, and 4 electrons. And the other possibility was sulfur dioxide. Everybody understands I'm switching these, right? I'm reversing them to be the oxidation reaction, correct? Producing sulfate plus 4 hydrogens, ions, plus 2 electrons. And we said, this cannot be the reaction because this is a reactant. Or it can only be a reactant for us. Another way to look at it is what don't we have here that we would need to be as a reactant for this reaction? I hear somebody whispering. What do we need for this reaction to be a reactant that we don't have?
Sulfur dioxide.
Thank you. We don't have this. So this cannot be the reaction occurring on the oxidation or anode side of our electrolytic cell. Can't be. Because we don't have the compound required for it. So this has to be the oxidation reaction that's taking place. Because water's everywhere, right? Does anybody have any questions so far? Now, so choose the answers by deleting what's not needed. We never did that. No, did we do that? So water surrounds the positive electrodes. Sulfate ions will be attracted to the positive electrode. We did that already, correct? I thought. Is that a duplicate?
We did it for negative and then this was positive.
Oh, okay. So we're kind of down here now, right? So number 8, as you can see, but water is both oxidized and reduced. Using the 2/2 equations, write the total cell reaction and calculate the voltage. All right, so I'm going to do that down here in bottom. So these are our 2/2 reactions, right? How many electrons do I have here? How many do we have here? How many times is this reaction going to take place? So we're going to have in our half reactions, we're going to have this 4 waters plus 4 electrons, giving us hydrogen plus 2 hydrogens plus 4 hydroxides. And for this, we're going to have 2 waters plus, arrow, producing oxygen, 4 hydrogen ions, just to say, and 4 electrons. Now, I know I said in last class, we're not going to balance reactions, but I kind of lied. You're going to balance some reactions, but this isn't nearly as involved as the ones we were doing, right? What's going to happen to the electrons? That's why we never see electrons written in our overall equations. This is going to give us 6 waters, producing 2 hydrogens, an oxygen, and 4 hydrogens, and 4 hydroxides. We're not done yet.
Can't you combine
Say it loud and proud.
the hydroxides and the hydrogen, and then it'll be water, and then that takes from the other side?
So that would give us 4 waters on the product side. Now what do?
Cancel or reduce.
Those go away completely, and this changes to 2. So our final equation is 2 H2O producing 2 hydrogens and an oxygen. That is our final equation.
Could you zoom in? It's really hard to see.
That make sense? Now, what was the E reduction for this half reaction? What's this half reaction's potential? 0.83?
Negative 23. Yeah.
And then this one was, what was it?
Negative 1.23.
So our E cell would equal our negative 0.83 plus our negative 1.23, give us a total voltage for of 2.06. Is that correct?
So do you not multiply the 0.83 by 2? You
No.
have to.
So on our voltages, so our potentials, They're a little bit different than what we treat Gibbs free energy, entropy, and enthalpy. So your potential that you look up off of the standard reduction potentials, you use those numbers as is unless you're reversing the reaction. The only thing you would ever do to those values is to switch the sign. You'll never multiply or divide. So it's independent, if you wish, of the stoichiometry. It doesn't matter what your coefficients are. Okay? Now, what warning did that just say?
15%.
Yeah, crap.
On the phone.
All right. Everybody, I feel like paparazzi. Everybody's taking pictures of it. That come out okay when you guys?
Mine's not loading.
Mine worked.
So, don't be weird.
What?
Okay. Now, so decomposing water, breaking water down into hydrogen and oxygen is an unfavorable process. We know that because we have a negative value for our voltage, for our potential. So that negative 2.06 says that this reaction must have energy put into it for the reaction to take place. Now, why am I using a 9-volt battery up here as my energy source?
If you just used a 1.5 volt, it wouldn't have enough voltage to carry out the reaction.
So if you got your AAA, your AA, C or D cell battery, even the D cell battery that looks like it's a chunky thing that could do anything, it's not going to do anything to this water because it doesn't have enough voltage to overcome the fact that that's going to be unfavorable. We require a 9-volt battery to do that. Or
You had like a 2.5 volt battery.
now, and that's actually a really good question because let's say that it was exactly, we knew perfectly well that was 2.06. We had to have that. Would a 2.06 positive battery make that reaction go? And the answer to that is no. You need more than what is required. Okay? So, I guess you say that negative 2.06, that's telling you the you've got to go just a little bit above that. Theoretically, anyway. Okay? Yes?
Does it either go or not go, or if you have 9 volt and 2.5 volt, would the 9 volt go faster or like more efficiently, or would they just go at the same rate?
That's going to depend on the battery design. Okay? What we're saying, and we'll let the physics people take care of the, what's going to be faster or not. But both of them, a 2.5 volt and a 9 volt, are both going to make that reaction take place. Or have the potential to make that reaction take place, right? How quickly it's going to go, that's going to depend on how many electrons that thing can produce all at once. Just because a 9-volt battery has more voltage doesn't necessarily mean it can produce more electrons. What it means is that it just has more potential to take place. Okay? that's why your difference in your triple, double, C, and D batteries, they're all 1.5 volt. But your AAA battery or cell is not going to be able to do some of the things that your D cell battery is going to do because it can produce more electrons all at once. It's going to have more current associated with it. Okay? Who's got questions? Now, really, the only thing that's changed here is that we're running the reaction backwards. The name of the cathode is still the same. The name of the anode is still the same. Oxidation and reduction. It's just we're forcing the reaction to take place. Any questions? All right. Next reaction. So go ahead and dump out this solution in the sink. Oh, wait a minute. Stir. Stir back. And what's it look like?
You still have to get this forward.
Oh. What's it look like?
The original. Pink. Orange.
Looks like the original. Why?
Because we mixed it.
Because you mixed it. You just read it. So the purple and the blue were due to hydrogen ions and hydroxide ions, right? Well, what do hydrogen ions and hydroxide ions do?
They form water.
They form water. So we just went back to deionized water, right? Question. Do we have the same amount of water in our petri dish as we started with?
No. I don't know. No, because no, we lost some.
Wesley?
Yeah.
Say it loud. Everybody listen to Wesley.
Go.
No, because there's byproduct of gas.
We changed some of that water into oxygen and hydrogen that went off into the atmosphere. Now, let's go back to those of you who are in one of the tech ed classes. When you guys made your little solar cars, you then used that to run an electrochemical cell because the reverse of this reaction, if I had hydrogen gas and oxygen gas reacting to them together would give us what? What voltage? Positive 2.06. Right? That's why all the research and stuff going into the electrolysis of water. Because once you got them separated out, you got an energy source there that's really clean and efficient. And what better? Solar cells. Yeah, it might be dirty to make to begin with, but once you make them, I mean, I got to calculate, my TI-30 solar is like 35 years old. I've never had to change a battery because it's solar, right? So up front, you got some, dirtiness to it, but you can continue to use that thing as long as it's, they do wear over time. I'm pretty sure that the solar cells that are in that are not as good as what they were when they were first made, but still runs the calculator.
How does a dam work?
A dam?
Yeah.
It's a wall.
Well, I meant like.
It stops water from, it makes it back up.
Hydro electricity.
Let's water first.
So, right. It just turns like a water wheel.
It's the same as like a wind turbine.
That's a good way of saying it.
The first question is so bad. Damn.
All right.
Me first.
I think you just wanted to say damn in class.
So go ahead and dump that down the sink, rinse it out, and for the next set of reactions we're going to do, you're just simply going to eyeball the amount And we just need enough solution that we're going to use to just barely cover the bottom. So pour a little bit in, shake it around, see if it's going to cover the bottom and stay covered, because we don't want to use too much. All right? I know it says to measure out 15 milliliters, but that takes too long. Just eyeball it, make sure you can cover the bottom, and you should be good.
Not bold enough.
And we're using the potassium bromide now, right?
Hey, Mr. K.
Yeah.
I like ran out and I don't have enough. We have some.
Scrounge.
Hand it over here. Like one Muller each be on.
Now I think in these instructions it tells you to use phenolphthalein. Do not use the universal indicator. Joe, phenolphthalein, not universal indicator.
Yeah, Mr. K, what if I
Even though it's Evan's fault.
It was Evan's fault. Mr. K, did you hear his question? What if you stick this in the outlet? Like, what would happen? Huge shock.
Not. Let's put it this way. Nothing good would happen. Okay. All right.
You know what I am?
That's what I'm saying. No, we're indexing that room.
Oh, don't worry about the index card. The only thing I would tell you is to make sure that you are keeping it very still when you're holding it in there. Okay?
Yeah, it disappeared now.
Me? Why would you say touching? Entering.
Now again, don't hesitate to use the magnifying glass.
Bubbling, bro. Yeah, you see bubbles in yellow or not?
Anyone not out of
Yo! They're attacking. Trying to break through the wall. Look from the stand, Mr. Gay. Very slight yellow there.
Okay. If you've got the yellow there now, if not, let it sit there for a little bit longer. But if you've got the yellow, go ahead and carefully take it out, and then carefully, get down there, walk a little bit, and see what you smell.
Wait, I'm actually allowed to smell it this time?
Maybe a little.
Sit in there.
No.
What does it smell like?
Ugh.
Expo marker?
It kind of smells like. It smells like the summer. It's a summer scent. It's a summer scent.
It's a summer scent. Well, yeah, kind of.
Right?
Or winter.
Okay, so not kind of.
Is this used in war?
What's that?
Is this used in war?
Hey, is this a bioweapon? You think if I smell this, we'll all pass out? Wait,
How do you do that?
would the indicator pick up on that?
All right.
Okay, do we want to what is it? Is it bleach?
Okay, so somebody said bleach. It's a similar smell to bleach.
Hey,
When I ask this question, some of you are going to go, oh yeah.
Yeah.
Does anybody have a hot tub at home?
Oh yeah.
well, yeah.
If you have a hot tub or if you've ever been to one, they smell like chlorine, but it's not chlorine, right? It smells different. Because hot tubs run, they use for the purification, they use bromine. So what you're smelling there, and you're probably going to get a little bit of an ethanol smell because phenolphthalein is made with ethanol, but you're also going to get a little bit of that odor from the bromine that smells a little bit like chlorine because where are they at on the periodic table?
They're pretty close.
Stacked on top of each other, so they get similar properties. Why chlorine's used in a pool, because bromine's more expensive. Okay? But the reason why you use it in a hot tub is that bromine is a liquid, chlorine's a gas. So the bromine will stay in the water and do its job longer, requiring less refills and stuff than using chlorine. If you use chlorine, you just have to continually put chlorine into the hot tub to make sure that the job's getting done.
So do we also want to use bromine and pools and not why not?
Because it's more expensive. And the chlorine will do the job at a lower cost than having to deal with bromine.
So basically, what happens when I drink hot tub water?
All we gotta do is look at you.
I walked into that one.
All right, so this yellow color that you saw, the yellow color that you saw, it's faint, but you can kind of see it here. That yellow color is due to the bromine being a liquid sticking around in the water there. What's causing the pink?
5%.
5% on the phone.
I'm gonna run out. Crap.
I have a battery if you want it.
Yeah, but I can't go from the battery from this to battery to the screen.
What?
His phone, I think he can't charge it.
I don't have the right kind of cable to do both. All right, now, so if we look at what's going on here a little more carefully, okay?
No.
So we've already established that over on in our electrochemical cell, this is where the oxidation is occurring, and this is our anode. So this is going to be what's happening here. What are we forcing to happen in our electrolytic cell? The reduction. Now, if you go and look at the table of possible reactions, for crying out loud. We got more now, right? So, but we can narrow it down to 4, or actually 3. The one involving bromine, that's a possible one. Because that's taking bromine ions, but this would have to be what? It would have to be reversed. So that's an oxidation. That would be occurring over here. So we could have 2 bromines producing bromine, I should say bromide, 2 bromide ions producing bromine and 2 electrons. Okay? Water's involved, so this is a possible oxidation reaction. So we could have our 2 waters producing oxygen, hydrogen ions, 4 of them, and 4 electrons. On the reduction sides, we're looking down here. Well, that's a possibility because we had potassium bromide, right? So we got potassium ions plus electron giving us potassium metal. And then our other possible reaction would be our water, because water is everywhere here. So 2H2O plus 2 electrons, is going to give us a hydrogen and 2 hydroxides. Which of these 2 reactions took place? The potassium or the water?
Water.
Because we didn't see any solid being produced, right? On this side, which of these 2 reactions took place? Now, I'm not saying, I'm going to be honest with you here. I'm not saying this reaction didn't occur at all. It's just not the primary one. Okay? Now, let's look at why. So, the potential for this reaction is negative 1.07. The potential for the water reaction is negative 1.23. Why is the reaction is negative 1.07, the one taking place, and not the one that's negative 1.23? Austin?
They're both unfavorable, but the negative 1.07 is more favorable than the other one.
You're going to go with the easiest one to make take place. And the bromine being oxidized is more favorable than water being oxidized. Like I said, it's not that we're not doing the water one, because I looked at mine carefully and there were a couple of bubbles, but not like we had before. Okay? This side here, we did see bubbles. We also saw the hydroxide being produced because we had the phenolphthalein. So we have the evidence for that. Okay? Who's got questions?